Okay, so it's my pleasure to announce Ujal Das, who is coming to us from Bilbao, Spain, from the Basque Center for Applied Mathematics. And I know Ujal since his time he was a postdoc at the Technion with Judah Pinschower. And today he will tell us about an optimal fractional Hardy inequality in the discrete on the discrete half-time.
Thank you, Matthias. Good afternoon, everyone. So first of all, I'd like to thank the organizers. I'm really happy to present this work here. Okay, so I'll talk about optimal Hardy weights for the fractional Hardy inequality over natural numbers. Okay, this talk will be based on my recent work with Ruben. So he is a PhD student at BCAM. Okay, so in this talk, our underlying space will be certain graphs over natural numbers. So the framework will be discrete. Okay. So let us first recall this discrete Laplacian over n, which is defined as this difference operator. So you take the differences of these functional values at n and n plus 1 and n and n minus 1 and then sum them up. So this is the usual Laplacian on n, discrete Laplacian on n. And if you see here, you have this n minus 1 term, and because of this n minus 1, you have to fix your functional value at 0, okay, to make it well defined. So we take it to be 0. So this is understood as some kind of Dirichlet condition in this discrete setting. Okay. Then clearly this discrete Laplacian on n is a bounded operator in this sequence space L2. And this is also self-adjoint. So since it is a linear operator on L2, you can represent it as an infinite matrix. And then if you do that, you get this nice form that on the diagonal, it has this 2, 2, 2. And just adjacent to the diagonal, it has this minus ones. So because of this expression, basically, you get this. And from here, you can more clearly see that this is indeed self-adjoint. So, okay, so we get that this discrete Laplacian on n is a bounded self-adjoint operator. And now we are interested in the fractional Hardy inequality, right? So what we want to do is to define the fractional powers of this Laplacian. Now, since this is a bounded self-adjoint operator, we will do this via spectral theory. Okay. So the spectral theorem guarantees that this discrete Laplacian, you can write it. So this will be unitarily equivalent with a multiplication operator. So this M, where the multiplier here, you can find that this is this multiplier 2 times 1 minus x. Okay, and the unitary operator is from small L2 to this weighted capital L2 space. And in fact, we know this unitary operator more explicitly in terms of these Chebyshev polynomials. Okay, so the Chebyshev polynomials are defined using this recurrence relation. So u0 is 1, u1 is 2x, and then it follows this recurrence relation. And it is known that these polynomials forms a orthonormal basis of this weighted L2 space. Okay, orthonormal up to this scaling root 2 by pi. So then this F is nothing but a orthonormal basis to orthonormal basis map. So this is the unitary map under which you get this representation. And because of this recurrence relation, this is elementary to get this representation. And now, basically, if you compare this with the full line case, so this F is basically the Fourier transform for this operator, right? Now, if you take Laplacian over the full line, Laplacian Z, then in this case, the usual Fourier transform from L to Z to so this is defined as basically if you take F So this is the discrete Fourier transform. And under this unitary operator, you can write this as again a multiplier here. So this you get like 4 sine square theta by 2. So here the multiplier you get is this function, the sine square function. Now if you compare this, that the sine square vanishes at 0, right? And here you see that the multiplier is 2 times 1 minus x, which is strictly positive in this interval. So this somehow indicates that probably this operator is kind of more positive than when you take the full line. So when you take the half line, the operator is, you can expect that this is becoming more positive. And that is indeed the case happens. Basically, you do not have Hardy inequality when you take the full line. Okay. So for the Laplacian operator on Z, we do not have Hardy inequality. So it is critical. But here you have the Hardy inequalities. Okay. So this is like theta by 2, you can say, like the variable. Okay. More positive in the sense this sign vanishes at 0, right? And that function is strictly positive in the. Okay. So anyway, so for the half line case, we have this representation. Now we wanted to define the fractional powers of this, right? So we'll just define these fractional powers just by taking the powers in the multiplier. Okay, so this is our fractional Laplacian, and we want to see the Hardy inequality for these operators. Okay, so let me define a slightly different thing here, which is called the graph Laplacian on n. So how it is defined? So you take a non-negative function on n cross n, okay, which is, I call it B. Now you can view this B as a graph on X. So basically how you do that? So take a non-negative function B, then let's say this is our natural numbers. So we take some other point, okay? So now suppose we have a B, then this B induces a graph on X by this. Let's say you take 2 points, N and M. If B and M is positive, you imagine that they are connected, you draw an edge, and this the value of B and M, you can think like this is the edge weight sitting on this edge, okay? And if B and M is 0, then there is no edge, okay? And so the standard graph, basically in the standard situation, you have n is connected to only to the 2 adjacent points, okay? N is connected to n minus 1 and n plus 1. Now, in this case, you can take this B as like B and M is 1 if M is either n minus 1 or n plus 1, otherwise 0. Okay, so this B induces this standard graph, basically. So this we will call as the standard graph, okay, on N. Okay, and then we want this tree property to be satisfied by B. So we take it to be symmetric. First of all, this we take it to be non-negative function. Then it has to be symmetric, meaning BNM has to be BMN. It has to be 0 on the diagonal, and it has to be locally summable. Okay, so meaning if you for each fixed M, if you sum it over N, this has to be finite. Then you take a non-negative potential, and then we define the graph Laplacian as this difference operator. Okay, so you take these differences and then you sum it over with respect to the weighted sum, where the weights are coming from this edge weights B, and the potential term we add here. Okay, so this is called the so-called graph Laplacian over N, where the graph, the associated graph is this BQ. Okay, so and why we introduce this graph Laplacian here is to basically use the so-called criticality theory on the graph Laplacian, which was developed by Keller, Finchover, and Pogorzelski. So for our results, we'll use some of the tools from this criticality theory of graph Laplacian. So our first task will be, so what we defined as the standard discrete Laplacian and the fractional Laplacian, that we have to now first represent as a graph Laplacian, and then we will use this criticality theory. Okay. So next I am going to do that we want to represent this discrete Laplacian as a graph Laplacian. Okay. So now if you see, so here, so So this was our definition of the discrete Laplacian on n. And if you see at n equals to 1, so at n equals to 1, you have just, this is just f of 1 minus f of 2 plus f of 1, right? Because our f of 0 is 0. And if you take n bigger equals to 2, so you have, so for any n bigger equals to 2, you can just write it as f of n minus f of m, where m is either n minus 1 or n plus 1, right? And if you combine these two, then you get this representation basically. So you can write it as extra potential because of this f1 sitting here. Okay, so now if you see, this is exactly in the form of a graph Laplacian, right? So you are taking these differences, you are summing it over some edge weights here, so which is basically 1 here, 1 when m and n is one distance away, and you have this potential term here. Okay, so this is exactly the graph Laplacian form over the graph. This, so now if you see the underlying graph is basically the standard graph, right? And the potential term is this delta 1. Okay, so now okay, so and this if you see this form of the graph Laplacian, for this we do not need to define f0 to be 0. Okay, if you see this f0 is 0 is encoded in this delta 1. Okay. Okay, so now we want to do the same for the fractional Laplacian that we have defined. Okay, so as I have mentioned before, the fractional Laplace operator also, you can view it as a matrix, where the matrix elements will be this. Okay, and then the action of this operator on some f, you can write it as this sum. Okay, and then this comes from just from the self-adjointness of the fractional Laplace operator. So this K sigma is symmetric. Now we want to write it as a graph Laplacian. So we just subtract these fn's and add this here. Okay, so we get these differences, but we need fn minus fn. So we just absorb this minus here. We get fn minus fm, and the potential term remains same. So okay, so if you see this last expression, this is almost like a graph Laplacian again. So you are taking these differences of fn minus fm, you are summing it over some edge weights, and you have a potential term sitting here. Okay, but we have to be little careful because we assume that our b sigma mn's vanishes on the diagonal, right? So we cannot basically directly take this as our edge weights. So this has to vanish on the diagonal. But if you see for n equals to m, this summand does not contribute anything to this sum, right? Because at n equals to m, this is 0. So you can just redefine your b sigma. For m equals to n, you can just simply take it to be 0. And for m not equals to n, you can keep it as it is. and then you get this expression. Okay, so this represent the fractional Laplace as a graph Laplacian form, but we have to be again careful that this we cannot still call it as a graph Laplacian, because we need to know that these coefficients, so this edge weights has to be non-negative and the potential has to be non-negative. Okay, and now how to see this as it can be non-negative? So these B sigmas are determined by this K sigma, right? Now if you see these K sigmas are here, okay, and if you write it down, so this K sigma is defined as this inner product in small L2, right? And this has this diagonalized form, which is F inverse. So this was defined as this, right? Using the spectral theorem. So this follows from the definition. Now, if F is a unitary operator, so you can simply write it. We can take the F to the other side. So FEN. Now this inner product is in the capital L2 space and weighted capital L2. So if you write it in the integral form, so this is nothing but, so this is the multiplication. Now f of em is this Chebyshev polynomials. So this is um minus 1. So you get a coefficient was there, 2 by pi, I think. And f of en is un minus 1. Then you have this weight. So this was defined as yeah. So this was en was sent to un minus. Okay. So this one. Okay. So yeah. And now okay. So now this would be just no square root. So now after some elementary computation, what you can see is basically this basic this k sigma will be negative if and only if sigma is between 0 and 1. Okay, so after 1, this changes its sign. Okay, and so this restricts us to consider only this exponent. Okay, because we want to see this fractional Laplacian as a graph Laplacian, and as we see that we can do this only for this exponent. Okay, and these computations also give you some asymptotics of this k sigma, which are important for us later. So this k sigma immense. So these are, I think, you will get 1 plus 2 sigma. If I'm, oh, sorry, that's subtracting. Okay. And another thing to notice here is that if sigma is strictly between 0 and 1, okay, then this B sigma Mn, they are strictly positive whenever M is distinct from N. So that means, okay, so recall that for the, when sigma equals to 1, for the standard discrete Laplacian, the underlying graph was the standard graph, right? And in this graph, N is connected to only 2 points. So the underlying graph is basically locally finite. Now here, for the fractional Laplacian case, if you see, the underlying graph is this B, and this B sigma Mns, they are positive for any distinct M and N. So this graph is not anymore locally finite. Okay, this becomes non-locally finite, and this basically causes a major problem to deal with this fractional Laplacian. Okay, so now we'll recall the main object of our discussion, so which is the Hardy inequality. So this inequality says that this quadratic form, which is associated to the energy of this discrete Laplacian, this can be bounded from below by this weighted L2 sum, where the weight is this 1 by 4 n square. Okay, and this was actually proved by Hardy in 1920s while he was answering a question by Hilbert regarding the convergence of a double sum. Okay, so Hilbert's question was uh, whether this sum is finite if an square is finite or not. Okay, where an's are non-negative. And using this inequality, Hardy gives a elementary proof of this fact. Okay. By the way, although this was proved in the discrete setting first, but we are probably more familiar with its continuum counterpart, which is given here, and also its higher dimensional generalization. And this is because the continuum part is connected to PD, harmonic analysis, and mathematical physics. For instance, the higher dimensional versions of this are regarded as some kind of uncertainty principle. For instance, the Heisenberg uncertainty principle can be derived from this Hardy's inequality, the higher dimensional version of this Hardy's inequality. Okay, so more is known about these inequalities. So for instance, this constant 1 by 4, in the both cases, this is known to be the best one. So this is the optimal constant. So you cannot improve this constant, okay? And there is no minimizer. So meaning that this does not attain equality for any non-trivial phi. Okay, so if we assume equality, it has to be, phi has to be 0. However, there are distinct things happens also when you go from the continuum case to discrete case. So for instance, it is known that 1 by 4t square, this cannot be improved in the continuum case. Okay. But when you go to the discrete setting, this 1 by 4n square, this can be improved. And this was found by Keller, Pinchover, and Pogorzelski. So I'll come back to this result. So now, if you see, so this leads to the question whether you can find the optimal weights in this inequality, right? So this is the question, whether we can find the optimal weights in this inequality. And this actually goes back to Agman in the continuum setting, and which was first addressed by De Vijver, Frass, and Pinchover in the continuum setting. And later, Keller, Pinchover, and Pogorzelski, they studied it in discrete setting. Okay. So, and I will come back to their construction, but let me first define the optimality of the Hardy weights precisely. Okay, we didn't define the optimality yet, so we are going to do that. So a Hardy, so you take a graph and you take a general graph Laplacian over the graph, and you take a Hardy weight W. By the Hardy weight, we mean a function W which satisfies the Hardy inequality. Okay. So for instance, in this case, this 4n square is the Hardy weight. Okay. So a Hardy weight W is called critical if you cannot improve this weight pointwise globally. Okay. So that means you cannot find a W tilde which is bigger equals to W, and W tilde is also a Hardy weight. You cannot find such things. Okay. So this is called the critical Hardy weight. And now let me recall this proposition, basically, which connects this functional inequality to the positive super solutions of the corresponding equations. Okay, so these are known as Agmon, Allegretto, Pippenbrink type principles. So this says that W is a Hardy weight. So that means you have this inequality, then you will have a positive super solution of this corresponding equation. Okay, and this is the if and only if thing. So whenever you have this inequality, you have a positive super solution of this equation. Okay, and W is critical. So when this Hardy weight is critical, you get that this equation will have a ground state, meaning that it will have a positive solution, and the positive solution will have minimal growth near infinity. Okay, so this is you can call it as a characterization of criticality, and we'll be using these two proposition, and this was proved by KPP in the discrete setting. Okay, so now so this was the definition of the critical Hardy weights. Now we want to define the optimal Hardy weights. So a optimal Hardy weight is nothing but which is critical and which is also null critical. So what is the meaning of null criticality here? So okay, so it is first, it has the optimal Hardy weight has to be critical. So now if you see this proposition, so since this is critical, it will have a ground state by this proposition, right? So let us call it capital phi. And then the null criticality means that if you take this sum, weighted L2 sum with respect to this weight, this Hardy weight, this has to be infinity. Okay. So what does this mean is basically, so criticality means you cannot find a pointwise larger weight. Okay. So, but this can happen if your weight is, let's say, very big locally at some point. Okay. But optimality means not only this, you need something more, okay, which is this condition. So this condition tells you that even your weight is large enough near infinity. So it cannot have a too fast decay near infinity. So if it has a too fast decay, then this would have been finite, right? So null criticality means your weight is even larger near infinity. So also null criticality implies this, so which says that your Hardy inequality, you cannot improve your Hardy inequality even near infinity, in the sense, in this following sense. So if you assume that you have this, you add this extra lambda here, and if you assume that your Hardy inequality holds outside a finite set, then this will imply that lambda equals to 0 if you assume W is null critical. Okay. So that means if our W is null critical, we cannot improve the Hardy inequality even at infinity. Okay. So this somehow says that, so if you look at this condition, this somehow says one is the best constant in this Hardy inequality, right? So like in this inequality, one is the best constant. So you cannot even, it is the best constant even near infinity. Okay, so you cannot improve it by 1 plus lambda. Okay, and this helps us to estimate the best constant in the Hardy's inequality, and we'll see how to get the best constant from this null criticality fact. Okay. Critical and optimal, right? No, optimal means first it has to be critical. Okay. So if you assume null critical means already critical, yeah, then yeah. Null critical can be defined only. Yeah, only if it is critical. That's true. That's true. Yeah. Yeah. So yeah. Now let me explain their construction, KPP's construction of finding a optimal Hardy weight. But first, let me give one construction how you can find Hardy weights. Okay, so getting a Hardy weight is not very difficult. So this comes from this proposition that I told, this Agmon-Allegretto-Pippenbrink principle. So basically, you assume that so you have a positive function which is superharmonic. Okay. So assume you have a positive superharmonic function. Then if you look at this equation, this is 0, right? So this is basically, sorry. So this is basically nothing. So if you take this is Laplacian u and they cancel, so you get Laplacian u minus Laplacian u. So this is 0. Okay. And these two conditions says you that this is non-negative. Okay. Now, if you recall the AAP principle, so if you recall this principle, if you have a positive solution, positive even super solution of this equation, then W has to be a Hardy weight, right? So here, this has to be your Hardy weight. So producing Hardy weight is basically comes from some super solution construction of the operator. Okay, so this super solution construction are quite crucial. But now the question is how you find the optimal ones, right? And this is they have found in this paper, and their construction says that so you take a connected graph. So this is your associated graph Laplacian. Now you take two superharmonic functions, okay, and which are harmonic outside a finite set, okay, and you take this quotient u0, and if u0 satisfies these two technical condition, then you can produce your optimal Hardy weights using this construction. Okay. So this, if you define your weight as this Laplace of uv to the square root divided by the square root, then this will always give you optimal Hardy weight. And let me tell this to condition, technical condition. So here u0, the quotient of this super solution has to be proper. So proper means, so if you take a compact set here, the pre-image has to be finite this side. So image of compact set has to be, pre-image of compact set has to be compact set. And this, if you look at this sub condition, so they means if X and Y is connected, then the value of this u0 at these 2 points cannot differ too much. So this is called the anti-oscillation condition, and this is the properness of u0. And under these two conditions, you have this optimal Hardy weight construction. And this construction works well in the locally finite case. So if your graph is locally finite, this construction is good. So because if when your graph is non-locally finite, if you see these two conditions, so in a non-locally finite graph, these two conditions cannot satisfy simultaneously. Okay, so this construction fails when your graph is non-locally finite. And if you recall, the fractional Laplacian we represented as a graph Laplacian, and the underlying graph became non-locally finite graph.
So which condition then?
These two conditions simultaneous. So if you,
What is the graph?
so this B is the graph with you. So your graph is induced by this B. And okay, so this B X.
UV are determined by the okay.
Yeah.
UV and then
Okay. And now you want to see this fact that how they have improved this 1/4 n square. Okay, just as an application of their construction. Okay, so we are in the standard discrete Laplacian case. So sigma equals to 1 here. And if you recall, I have already mentioned that the underlying graph was the standard graph. So this is a perfect non-local locally finite graph. So we can apply their result. So we take this function, identity function u, and you can verify that this is a harmonic function on natural numbers. And this, you take this constant function v, which is 1. You can verify that this is superharmonic on n and harmonic on n minus 1. So these two conditions satisfied. So u and v is superharmonic, and they are harmonic outside a finite set. So these two functions satisfies their condition. And now here v is just 1, right? So your U0 is U by V, which is again 1 here, which is U exactly, right? So U0 is nothing but U here, okay? U0 is U by V. So here it's just U because V is 1. And this is identity function. So this is proper. This is locally finite graph. So anti-oscillation condition is also satisfied. So you can apply their construction.
Supreme is not finite, you know? Or it's
So,
finite.
so this, because this is n is connected to n minus 1 and n plus 1. So the supremum cannot vary too much, right? So this is either
Connected with label.
The name.
You take supreme not on all it's why. Okay.
Yeah.
You don't
Yeah.
sense of the
Sorry.
topology.
Yeah. So this is when BXY is positive. Okay, so you can apply their result. So this their result says that this has to be optimal. So here V is just 1, right? So this turns out to be this, and you can exactly compute what it is because U is just n. And if you compute, it takes this form. And if you expand, you get this, where the higher order terms are all non-negative. So basically, if you see, they have improved the Hardy weight. Okay, and this is known to be optimal. So you cannot globally improve this weight. Okay. Okay, so now, so our interest is to see the fractional analog of it. So we take the fractional Hardy inequality, and we want to see what are the optimal weights in this inequality. Okay, let me give some of the context of this. Okay, so when you go from the continuum real line, so continuum case to the discrete case, you have some distinguished phenomena, and also when you go from the half line case, full line case to the half line case, you have some distinct things. So for instance, so if you take the full real line case, full real line, then you know that the Laplace operator on the full real line is critical. So you mean, so what I mean, that we do not have Hardy inequality on the full line R. But if you take the fractional powers of it, they become subcritical up to the power half. Okay. So, and this is if and only. So after half, this becomes critical. And you have a complete analogous phenomena if you go from the continuum case to the discrete case. So here also it is known that the discrete Laplacian on Z is critical. So this, as I mentioned at the beginning, that discrete Laplacian is critical. So you do not have any Hardy inequality on the full integer. But if you take the fractional powers of it, they become subcritical, again up to the power half. Okay. And in this recent paper, Keller and Yeatsman, they have found, so subcriticality means, subcriticality just tells you that you have Hardy inequality with respect to some weight, some non-negative, non-trivial weight. And Keller and Yeatsman found the optimal Hardy weight in this case, okay, for sigma less than half on the full line. Now, when you go to the half line case, so in the continuum, you know that these fractional powers are subcritical for any sigma between 0 and 1. And also, if you take any integers powers, they become subcritical. Okay, but when you go to the discrete half line case, which is the natural numbers, now if you take the fractional powers, they become subcritical if and only if sigma is less than 3 by 2. And this is this surprising fact is recently observed by Gerhard, Krecherick, and Stamper. So if you see now, the distinction is here, right? So if you are in the continuum half line, so any powers, any integers powers is subcritical. But when you are in the discrete half line case, this is subcritical only up to 3 by 2. So after 3 by 2, it is critical. So you do not have Hardy inequality in this case.
But what, if you're the continuous case,
Yeah.
if you take sigma bigger than 1, but not too big.
Yeah, so this, I don't know that there is no result yet, I think, in that case, like the sigma 1 to sigma fractional, but
So this corresponds like to take the function in HS and divide it by x to the s.
HS
like S equals 1 is the classical.
Yeah. Mhm. Yeah, but I am not aware of any results from sigma, like the fractional, but in between two integers. So,
Sum of root of rank helps.
okay.
I think you would. No, so this is like, they, morally, it's like the norm HS is equivalent to the division by this, like X to this.
Uh-huh. Yeah.
And then if, and then you have a limitation that is if S is not too big, specifically not above 3 abs. So between 1 and 2. It is related to traces. 3 halves will have another trace. You're continuous.
Okay.
Okay.
Yeah, we can discuss that. Yeah. Okay, and so and not only this, so they have this Gerhard Krecherick and Stamford. They have actually found an hardioid, which is this one. But okay, so but nothing is known that so they in fact asked this question whether this weights has the best decay, and also these constants these are not explicit, so whether you can get some estimates of this constant. Now our goal is to find the optimal hardioids, and if you find the optimal one, these two questions are answered like just as a corollary. Right, so optimal one means it will have the best decay, and now you can get some estimates of this constant as well. Okay, and the strategy I have already told what is our strategy. So we already expressed this as a graph Laplacian. Now we'll use this criticality theory of KPP to prove that to find some optimal hardioids.
So sigma is from the
Sigma is 0 and 1. So we
0 and 1.
Yeah, because we could represent it as a graph Laplacian only up to that. Okay, so and as you recall in the construction that the super solution plays a crucial role. Okay, so the first thing is to look for is the super solution for this fractional operator. Okay, so this is what we are going to do. So now you take this complicated looking function I alpha, and this turns out to be positive, and this is actually the Green's function for the fractional Laplacian. And this is not difficult to see that this would be your Green's function. This is because if you see, if you recall the multiplier for our fractional Laplacian, so the multiplier was this, right? So the multiplier was this, right? And this Green's function is kind of the inverse of the fractional Laplace, right? And if you see, we take the inverse powers of this multiplier and we define this operator. We define this function, and this turns out to be the Green's function for this. But then one can anticipate, okay, so you found a super solution, which is the Green's function, then whether you can apply the KPP's construction and get a hardioid. So, I mean, so you can anticipate that your optimal hardioid could be this, right, by their construction. But the problem is, as I mentioned again, that this graph is not anymore locally finite. So you cannot directly say that this is the optimal hardioid.
So can you go back? So what did the differentiate when found?
That this is the hardioid. Yeah.
How do I put maybe not?
Maybe not. Yeah, that is what we are trying. We are somehow trying to prove the quantitative version of this. Like in a sense, we are finding the optimal ones in this inequality. Okay. Yeah, so we cannot directly apply KPP's construction for this because this is not locally finite. However, these I alphas, they satisfy very nice identity. Okay, so if you apply this fractional Laplacian on I alpha, you get back I alpha minus sigma. Okay, and if you write it just like this, okay, so you can write this as this. I alpha cancel and this is 0. So now if you again recall the Agmon Allegretto Pippen's principle, so these are, so you get a positive solution of this equation. Okay. So as long as this is a graph Laplacian, you can use this Agmon Allegretto Pippen rings result and you can conclude that these are your Hardy weights. Okay. So you automatically get a family of Hardy weight as long as this is the graph Laplacian, which it is if sigma is between 0 and 1. Okay, so if sigma is between 0 and 1, we found a class of Hardy weights for this fractional Laplacian. But now we have to look for the optimal ones, right? We have the class of Hardy weights. Now, which is the optimal one? Before that, if you see this weight, so this is just I alpha minus sigma by I alpha. And you can actually compute some asymptotics of these I alphas from this relation. Okay. So they are known to be, so I alphas. Okay. So I alpha in they are either asymptotics or two-sided equivalent to 2 minus 2 alpha. Okay, so they has these asymptotics, and you can explicitly compute this W alpha sigma, and which takes basically this form in terms of gamma functions. Okay, and so this is the n-dependent term, and you can find the asymptotic of this, and which is exactly 1 by n to the 2 sigma. Okay, and if you see, this is what yeah, yeah, as they have, yeah. And this is the purely constant, which depends on alpha and sigma. And now the point is that this attains its maximum at this particular point when alpha is 3 plus 2 sigma by 4. So you see that we have a family of Hardy weights which has the same asymptotics as 1 by n to the sigma. And in front of them, this constant is the largest one when we have 3 plus 2 sigma by 4. So you can suspect that this has to be the optimal one, right? And which is the thing what we get, this is the optimal one. Of course, this is not the proof. So you have to prove that this will be critical and null critical. Okay. So before going to give the ideas how you prove critically.
The constant is better.
Yeah. So
For one half. One half.
uh,
We have a different constant.
no, they didn't have any constant. So this is just some gamma, and they asked this question like, okay, can we give some estimates or can we find the best gamma? Okay, and if you see from our result, it is immediate that this gamma has to be less equals to this constant. This follows from the null criticality. Okay, so because they have the same asymptotics as their weights, and this is the optimal one. So null criticality says that you cannot improve this even at infinity, right? So I already told this that null criticality means you cannot improve by 1 plus lambda. So that means you cannot improve this constant. So gamma has to be less equals to this.
Why did you sigma one and one of four?
Sigma equals to?
Sigma equal to one.
So yeah, so that I'll come to that. So okay, so okay, maybe let me first say this. Okay, so now if you take sigma equals to 1, so you get this weight. Okay, and you get here 9 by 64. Okay, and now let me go back to the KPP's weight. So if you go to KPP's, this is 5 by 64. Okay. So in near infinity, our weight is bigger than KPP's weight. But you cannot really obviously you cannot compare them because both are optimal. And it turns out that WKPP at 1, this is bigger than this, okay? Okay, so now so we have to prove that this is critical and this is null critical. So let me give some ideas how we prove criticality in general. So criticality means we have to prove that we cannot improve this weight by a non-negative, non-trivial function. So you assume that we do improve it, and then we have to prove that this W tilde is 0, right? So you assume this inequality, and then you send this W to the W optimal to the other side, and you call this as Q. Okay. So now suppose we have a sequence of function phi n for which this Q phi n goes to 0 and phi n goes to some pointwise goes to some positive function. Then you can show that using just Fatu's lemma that this side will be less equals to limit of this. And limit of this, you assume that this goes to 0. And this is non-negative, this is assumed, and phi is a positive function, this also we assume. So this is also non-negative. So you will get that W tilde is 0. So as long as we find such a sequence, we can prove that this W tilde is 0. And this sequence are called the null sequence. So the proof remains how to find such a null sequence for Q. Okay. And this we find using some ground state transform of Q. Okay. So that I am skipping it. Okay. So now let me, in the remaining time, let me tell one of the application of our result. So this we have recently learned that if you have find the optimal Hardy weights, and if you know the ground state, asymptotics of the ground state, then you can get some unique continuation results. And these unique continuation results are connected to this conjecture by Landis, so which is given here. Let me explain this conjecture. So if you take a bounded potential V, and if you take this Schrodinger equation, then Landis claimed that if you take if any solution U which decays like this exponential, that k is strictly bigger than 1, then it has to be identically 0. Okay, so this means any non-trivial solution of this equation cannot decay super exponentially. Okay, and we with pinch overs, I have worked on this conjecture in the continuum setting in RD, and with Keller and pinch over, we have it in the discrete case, and this is our result in the ZD case. What we found that so you take this Schrodinger operator, but we assume that this is non-negative operator. So this is because we want to use the criticality theory, and that's why we had to assume that this is non-negative. Okay, and under this assumption, so if you take this V is bounded by 1, then if our solution satisfies these two decay, then we could prove that U is 0. Okay, and if you see these two decays, so these are actually weaker decay than what Landis has proposed in his conjecture. So in Landis's conjecture, this is e to the kx, or k is strictly bigger than 1. And here, if you see, this is some polynomial decay, and this we need some exponential decay, but still it is weaker than Landis's conjecture. But okay, this does not solve the conjecture because we assume that the underlying operator is positive. Okay, but what I wanted to say, how we get these two decay is basically this comes from the ground state of a optimal corresponding to a optimal Hardy weight. Okay, and this decay we get from the Green's function of so the first decay is the first decay corresponds to a ground state of optimal Hardy weight, and the second decay comes from the decay of the Green's function of Laplace plus 1. This 1 is basically because of this 1. Okay, Now, okay, so on the half line, now this was the result on ZD. So now, sorry, yeah, D greater or equals to 3, yeah, greater or equals to 2, yeah, and so now in this case, so we already found the optimal Hardy weights, and we know the asymptotics of the ground states. So we just use our previous ideas to get some unique continuation result as an application, and what we get is basically this. So here we assume V is less equals to 0. This I'll tell why we assume this. And under this assumption, we again assume that the underlying operator is positive, and then we have, if U satisfies these two decay, then U has to be 0. Again, this comes from the ground state of the optimal Hardy weight what we have found, and this comes from the Green's function of this. Okay, this we know, and now why we assume this is basically we couldn't find the asymptotics of Laplace plus 1. Okay, we didn't try hard enough also to find it, so we just wanted to give some application, and we give this rule. Okay, and so what is left is basically how to do this for 1 to 3 by 2. So we need, I think, completely different ideas because we cannot use this criticality theory in this case, and this is completely open. Here are the references. So this is our paper. This is the paper by Gerhard, Kracherik, and Stampak, where they found this surprising criticality transition. This is the paper by KP, where you find the construction. This is the paper by Keller and Nietsman, where they found the optimal Hardy weight for the fractional Laplace on Z, on the full real line Z. And here you can find this unique Landis type unique continuation result. Okay, so thanks for your attention.